All right, everyone, welcome back. So, in our last explainer, we looked at rectifiers with simple resistive loads. Today, we're taking a huge step forward into a much more common and way more interesting scenario, the single-phase full-wave rectifier with an RL load. This is really where the theory starts to get real.
Okay, so here's our game plan. First, we're going to talk about why we need to move beyond simple resistors. Then, we'll see exactly what adding an inductor does to our circuit. This leads to two totally different ways the circuit can behave, and we'll dig into both. After that, we'll figure out how to predict which mode we're in, and finally, we'll tie it all together with a real practical example.
You know, with a purely resistive load, things are pretty straightforward, right? The current just follows the voltage. Nice and simple. But in the real world, almost nothing is a pure resistor. Think about a motor or a big power supply. They all have some inductance. And that inductor, well, it changes everything.
So, this is the circuit we're going to be digging into. It should look familiar. It's our standard full-bridge rectifier. But look at the load. That's what's new. We've got our resistor R, but now we've added an inductor L and a DC voltage source, E. Now, what's that E doing there? Well, you can think of it like the back EMF from a DC motor that's spinning. This is a very realistic model for the kind of loads we actually want to power.
So what's the big deal with this inductor? What does it actually do? Well, the whole job of an inductor is to resist changes in current. It's kind of like inertia for electricity. It does this by storing up energy in its magnetic field. Let's see what that looks like.
Now check out these waveforms. On the top, that's our output voltage. Looks just like it did with a resistive load. But look at the bottom graph, the load current. Whoa! It looks completely different. See how the current doesn't crash down to zero every time the voltage does? That's the inductor doing its thing. It's releasing that stored energy to keep the current flowing, smoothing everything out. So this energy-storing behavior, it's so important that it actually creates two completely different ways the rectifier can operate. Which mode you're in depends on your specific circuit, the values of L, R, and that DC voltage E. We call these two modes continuous and discontinuous conduction. First up, let's talk about the continuous case. This happens when your inductor, L, is big enough. It basically acts like a big energy reservoir, storing enough juice to keep the current flowing through the load for the entire AC cycle. The key thing here is the current never drops to zero.
And here is a perfect picture of that continuous current waveform. You can see that the current I.O. always stays above that zero line. It dips down to a minimum value and up to a maximum value, but it never stops. What you've essentially got is a nice steady DC current with a little bit of AC ripple riding on top of it.
Now, this isn't just a pretty picture. We can actually nail this down with a precise mathematical equation. This formula here lets us calculate the exact value of the current at any point in time. It takes everything into account: the AC source, the resistance, the inductance, the whole shebang. This is the tool we need to analyze the circuit's performance.
But what happens if your inductor is a little on the small side? Or maybe your load resistance is really high? Well, in that case, the inductor might not be able to store enough energy to keep the current going all the time. And that's when we enter what we call the discontinuous mode.
You can see the difference right away. The current kicks on at angle alpha, which is when the input voltage gets high enough to get things moving. The current rises and falls, but then, at this angle we call beta, the extinction angle, the inductor runs out of gas. The stored energy is gone, and the current just flatlines at zero until the next voltage pulse comes along to start it all over again. So, to analyze this mode, the whole game is about finding that extinction angle beta. The only problem is, it requires solving what's called a transcendental equation. Now, don't let the fancy name scare you. All it means is that the variable we're looking for, beta, shows up both inside a trig function and outside of it. You can't just solve for it with simple algebra. We have to use computers or lookup tables to find the answer. And since trying to solve that equation by hand is a real pain, we often use tables like this one. Think of it as a cheat sheet. It shows you what the extinction angle beta will be for different circuit conditions. It all depends on the voltage ratio X, which is just the DC load voltage compared to the peak AC voltage, and the load impedance angle theta, which tells you about the relationship between your inductor and resistor. Okay, this brings us to a really important question for any engineer designing one of these circuits. How do I know which mode my circuit is going to operate in? To figure that out, we need to find the dividing line, the exact boundary between these two types of behavior. In this graph, this is basically your design map. It's super useful. All you do is calculate your load's impedance angle, theta, and your voltage ratio, X. You find that point on the graph.
If you land in the area above the curve, congratulations, your current is continuous. If you're below the curve, it's going to be discontinuous. It's a fantastic tool for predicting how your circuit will behave.
All right, enough theory. Let's get our hands dirty and put this all into practice. We're going to walk through a real example straight from the textbook to see how all these ideas come together to solve an actual problem.
So here's the typical process you'd follow. First, you calculate the basic load parameters, like impedance. Then, and this is the key step, you make an assumption. You assume the current is continuous. Why? Well, frankly, the math is just a lot easier. So you run with that assumption, calculate the current, and then you check your work. If the current you calculated never drops below zero, then bingo, your assumption was right. And from there, you can go on and calculate everything else you need, like average currents and the power factor.
Now, to make sure our calculations are on the right track, we can always use some help from simulation software, something like PSpice. For this exact same circuit in our example, PSpice predicts that the average output current is going to be 31.83 amps. Let's see what that actually looks like.
And here it is, the visual proof right from the simulation. That top plot is our instantaneous output current, and the bottom is the voltage. As you can see, the current is definitely continuous. It never hits zero. And the average value from the simulation, about 31.8 amps, is incredibly close to the 32.8 amps we get from our equations. This is great. It tells us our analytical approach works really well.
So let's just boil this all down. What are the big things to remember? First, adding an inductor totally changes the game by smoothing out the current. Second, because of that smoothing, we get two completely different ways the circuit can run, continuous or discontinuous, and we now know how to figure out which one we're dealing with. And maybe the most important point of all, you have to know which mode you're in before you start doing any math, because the equations you use are completely different for each one.
Okay, that leaves us with one last thing to think about. We've done a great job smoothing out the current with our inductor. But if you remember that voltage waveform, it still had a massive ripple. It was super bumpy. Now we know an inductor is a component that opposes a change in current. So, what component do we know of that opposes a change in voltage? And what do you think would happen if we added one of those to our circuit? That right there is the next big step in building a truly great DC power supply.